Hey guys, we're going to go through lesson 3.2. This is just kind of an extension of exponential and logistic functions like we saw in lesson 3.1. So we're going to start with a formula that could represent growth of a population. And when I say a population, I mean that could be growth of a population of people. It could be growth of a population of bacteria. It could actually also represent a population in terms of like money. But this is for an exponential growth. So let's say if a population is called P, so population is called the letter P. If it's changing at a constant percentage rate, and the percentage rate we're going to call R, so that's your percentage rate, then we're going to use this formula to model that population at any given time. So again, T is going to represent the time of whatever the scenario may be. In this formula, again, P of T over here will equal the population at some set time. P sub 0 is going to be the initial population. P sub 0 is the initial population, which is like the starting population. R is going to be your percentage rate, but you're going to write it as a decimal. And then T is your time. So we're going to start with something real easy. Let's first start with looking at problems that have already been created and turned into an exponential model fitting this setup. And let's talk about whether it represents exponential growth or exponential decay. So when we look at these two formulas, they both represent the population of certain towns. And it just simply says, tell whether the population model is an exponential growth function or an exponential decay function. So I'm going to show you how to do this with a graph, and I'm also going to show you how to do this without one. So let's start with a graph. So with a graph, you would just simply go to something like Desmos, and you would be looking for either a growth curve or a decay curve. So for the Surfside function, instead of writing P of T, I'll just write it as Y equals, and then 102,324, and then the inside number was 1.025, and then instead of to the power of T, I'll write it as to the power of X. Get it to work. Okay, now I can't see it because my graph is zoomed way in, and this is a really big number, so I'm going to have to zoom way out to find it. There it is. So you will see that it starts out small and increases really fast, so that means that's an exponential growth. So let's go back to the notes, and we're just going to write exponential growth. Now, there is a way that we could tell that this is exponential growth without making a graph. And the way you're going to do that is you're going to look right inside of the parentheses. And you're going to remember two things. Remember that this first number at the beginning is your initial population. But more importantly for this question, you need to remember that this inside number is created by taking 1 plus the growth rate, but as written as a decimal. So we're going to break this down so that it looks more like the population model. So if I wanted to say what 1.025 is broken down, we could say that that is equal to 1 plus 0.025, right? And then we could keep going further and say, well, this is supposed to be the percentage growth or decay rate as a decimal, right? Well, what would this be then as a percentage? We'll move the decimal point 2 times, and you'll get a percentage rate. So basically, because we're getting a positive value, because it was 1 plus, that means that our function is a growth function because we have a positive percentage rate. So let's try this second example. I'm going to do the second one without Desmos just to show you how that works. So Mountain View, population, there we go. Population is 86,500. That's your initial population. 0.92. Well, to fit my formula, I have to have 1 plus something to get 0.92. And the only way to get 1.92 if I'm starting with 1 is to subtract 0.08, right? 1 minus 0.08 would equal 0.92, wouldn't it? And then if you had to turn negative 0.08 back into a percentage, it would be negative 8%, right? So when you see the negative, that tells you that you actually have an exponential decay. And in the case of our problem, that would mean that the population of this town is actually decreasing, okay? So this one would actually be an exponential decay. The population is decreasing there. Okay, here's another example. It says just determine the exponential function with an initial value of 12 that is increasing at a rate of 6% per year. So basically, we know P sub 0 is going to be 12, and we know that the rate is 6%, but we're going to write the rate as a decimal. I also know that my rate is a positive number because it says that it is increasing. So we're just simply writing the function. And if you know the setup of your exponential population model, then all you've got to do is identify P sub 0 and identify R and plug them in. Okay, that's all you have to do. So for P sub 0, it said that was 12. R, we said, is positive 0.06. T is a time that'll change, so we'll leave it as T. And we're going to do one more easy step, which is just to add and simplify the numbers in the parentheses. So that would be equal to 1.06 to the power of T. That's it. All right, so here's like a sciencey question. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 250,000. So we know how much we're starting with, right? It doesn't say it specifically, but it does say that we're starting with 100 bacteria. So that would represent P sub 0 here. The rate is interesting. So the rate, it does refer to a rate as it doubling every hour. But it's kind of hard to put that into a percentage, a number to plug in. So when you double something every hour, you're basically raising it by 100%. Okay, doubling. So maybe make a note of this. Doubling is equal to raising it by 100%. So what you're going to do, you can think of it two ways, is you're going to plug 1 in for your rate because 100% as a decimal is equal to 1. Or you could think of it a little bit simpler in that you're going to be multiplying what you're starting with by 2, but you're multiplying by 2 every hour. So T will change and raise it exponentially to represent the multiplication of 2 every hour. So change R to 1, or you could think of doubling as multiplying by 2. Either way, it doesn't matter. So what is this number then? This 250,000. Well, this is what we wanted to end at. So we're going to call this P of T. And it's called P of T because it's the population at some unknown time. So we're saying the population is going to be 250,000, but we don't know when that's going to happen. So we're going to plug in 250,000 for P of T, and we're going to find the time T. So this is an equation now that we're going to solve. To do that, we're going to begin by dividing by 100, which is just like canceling zeros. So that's 2,500 equals 2 to the power of T. You're going to then grab a calculator, and you're going to figure out 2 to what power equals 2,500. If you don't have a calculator or you just don't want to play the guess and check game, you can also use our best friend Desmos. So let me show you how we're going to do this on Desmos. By the way, graphs can help you solve literally any equation. So like this particular equation, I want to know when 2,500 is equal to 2 to the power of T. So I'm going to graph on Desmos y equals 2,500, And I'm also going to graph y equals 2 to the power of x, not t, because I'm on a graph and I need x's and not t's. Now I can't see the whole picture here because obviously I just plugged in a really big number. So I need to go up. Remember, you could also play with the x and y values here. Maybe I'll do that this time. So I need my smallest y value to be like 2,000 and maybe up to 3,000 so I can see this 2,500 line. But do you see how our blue line is the exponential and the red is the 2,500? Well, if I want to solve this equation here, all I need to do is see where those two things cross. Okay? So they're crossing at 11.288 and 2,500. So let me write that down real quick. They cross at 11.288 and 2,500. And so what this means is that when the time is 11.288, the population will be 2,500, okay? Or solving the equation, I suppose, the time to solve the equation would be the x value. So we're going to say t is equal to the x value, which is 11.288, and that was representing hours in this question. Okay. I know this skips around a lot. We're skipping a lot of questions. So let's go to this one. So this is a little bit different because it's not an exponential population model. You can tell by the way it looks. This is actually one of our logistic growth models from lesson 3.1. So you may want to take a minute to go find those notes to make sure you understand what each thing in this setup represents. Real quick, the top number in the logistic growth function is called the carrying capacity. Oops, capacity. And then you still have things like T for time, and then there's rates and decimals and stuff. But this logistic growth function is something we use when we have like a maximum capacity possible. So like we can only fit 1,500 students in the school, or we can only sustain so many people in this population based on resources. Back to the question. So it says Surfside High School has 1,500 students. Max, Patty, Juan, and Andrea start a rumor which spreads logistically or exponentially so that this function here models the number of students who have heard the rumor by the end of T days. So S of T is the number of students that have heard the rumor on whatever day, T is days. And again, in your function here, 1,500 is the carrying capacity. So basically, that's the most number of people in the school that can hear the rumor, right? Everybody would be 1,500. So the first question says, how many students have heard the rumor by the end of day 0? So we're going to very simply just take 0 and we're going to plug it in to the logistic growth function for T. So it's going to look really funky at first. And we're going to not freak out. This is how it looks. And then we're going to simplify. So let's start small. What happens if I take a number and multiply by 0? You get 0. So you're going to have 1,500 over 1 plus 38. E, remember E is just like 2.718. Just means it's a number. All right, and then let's go back to something small. What's e to the 0 power? What's anything to the 0 power? That should equal 1. So I can simplify this a whole bunch now because I know that this whole exponential thing is just 1. So that's 38 times 1, which is 38, plus 1 makes the whole bottom 39. And then you can just grab a calculator to do 1,500 divided by 39. But I think it's about, I don't have the exact decimal in front of me, but I think it's about 38. And that would be the number of students. So these 4 kids start a rumor, and by the end of the day, 38 students know about it, which truthfully, I feel like it would actually be a lot more than that, right? High schoolers tend to love rumors, don't they? Next question, and actually this is the last one in our lesson. This is a short one. How long does it take for 1,000 students to hear? So 1,000 is going to be, in this problem, S of t. So that's what you're going to set your equation equal to. And you're going to be finding the value of t. Okay? Now, keep in mind that when you set up this equation, it's complicated, right? You cannot, with what your current knowledge base, you cannot solve this by hand. So instead, what you're going to do is you're going to use your friend Desmos to help you. So I'm going to show you one more time. I'm going to solve this equation on Desmos by writing y equals 1,000 as a graph and y equals this whole big fraction thing as a graph. And I'm going to look to see where those two equations or functions cross. So to Desmos, here's my 1,000. It's still zoomed in from the other question that we did. So there's 1,500 plus, get all this stuff ready. Make sure that you change the t to an x so that it will work on the graph. I'm already zoomed in from the last question. I'm going to hit the home button to take me back, and then I'll just kind of find my way. But I need to see where these lines cross. So there's my blue exponential, or sorry, logistic function. Come back. Oh, and we're going to 1,000. So I guess I better just maybe change the y values to get there a little faster. Maybe I'll go 900 to 1,100. There we go. And I want to just know where they cross. So they're crossing at 4.812, and 1,000 is the population. So the time would be equal to the x value, which is 4.812, and that is days. So basically, by the end of the 5th day, 1,000 people know about the rumor. So it doesn't take very long for rumors to spread. Remember that you are required to take notes over this video as part of your grade for the week. You also have an assignment to do over this lesson.